Hello, this is Harrison Newman, and today we're doing video assignment 3C. This one is about air conditioners, heat pumps, and the efficiency and pollution caused. The efficiency of air conditioners and heat pumps are highly dependent on the temperature difference between the hot air and the cold air. Now, this means that depending on where you live will heavily influence the efficiency because different places obviously have different climates. And further, the way the electricity in your walls is being produced may be different. Due to solar and wind power, the way your power is being produced may even vary by the time of day. Assume the heat pump has a Carnot efficiency of 0.25 or 25%, and in California, the daytime electricity requires zero point 0.2 kilograms of CO2 per kilowatt hour, and the nighttime electricity requires zero point 0.4 kilograms of CO2 per kilowatt hour. Let's say you need 40 megajoules of thermal energy to heat your home in a 90% efficient methane furnace. First, what is the actual number of megajoules produced to get the 40 megajoules inside if it's at 90% efficiency? So, we make a little equation which is simply 0.9x plus 0.1x is equal to 1x, which makes perfect sense. You turn the 0.9x into 40 megajoules because that's what it represents, and you just solve the equation from here. What you get is that x is equal to 44.4 megajoules. If you look at the diagram of the house I drew, you'll see that for a 90% efficient furnace, you have 10% of the heat just leaving the house, which in our case is 4.444 repeating megajoules, and 40 megajoules entering the house, which is the 90%. Now, if we'd like to figure out how much CO2 is produced by this process, we first have to look at the reaction between methane and oxygen. C3H8 combusts with oxygen as in the reaction shown below. C3H8 plus 5O2 yields 4H2O plus 3CO2, which means that for 1 mole of C3H8, we're going to get 3 moles of CO2. So, how many moles of C3H8 actually produces 44.4 repeating megajoules? The enthalpy of combustion for C3H8 is 46.3 megajoules per kilogram. We plug that into the equation we have below, and we get 0.96 kilograms C3H8. Via stoichiometry, we convert the kilograms to moles, which is 960 grams C3H8 times 1 mole of C3H8 per 114.2 grams of C3H8. And that's the inverse of the molar mass, which would be 114.2 grams per mole. Multiply it then by our 3 moles CO2 per 1 mole C3H8, and we get 25.2 moles of CO2. And it's kind of hard to understand exactly how much 25.2 moles is, so we can convert this using the molar mass of CO2 to get 1.11 kilograms of CO2. To understand the heat pump or the refrigerator, it is a little bit easier to try and understand how the heat engine works first. So in a heat engine, we have a heat reservoir at temperature H or TH, which is going to be the hot temperature. And usually in a heat engine, this is provided by something such as combusting gas or like gasoline or coal or something similar. Now, this delta QH is going to go through some process which extracts delta W, which is some amount of energy from that heat. And the rest of it then is exhausted as delta QC into the cold reservoir, which in most cases is basically the atmosphere. Now, the heat pump works the opposite to this, and it kind of makes it very much more efficient, and it's almost kind of like a miracle in a way because you take the cold reservoir TC, move a certain amount of delta QC, which is taking heat out of the cold reservoir for a smaller amount of work than you actually get heat from the cold reservoir. Then you combine the work and the heat you've extracted from the cold reservoir to get the delta QH, which is the heat energy you are putting into your heat reservoir, which in many cases would be something like your house or a car or somewhere where people are residing. Because these two things work this way as opposites of each other, they're both reversible processes being done in reverse. For the Carnot heat engine, we have an efficiency that is defined as eta Carnot equals 1 minus Tc over Th. And we can, through very simple algebra, turn this into delta T over Th. Now, what this means is that typically the delta T is going to be much smaller than Th, and the efficiency of your Carnot engine is going to be much less than 100%. Because a heat pump is this in reverse, Eta of the pump is equal to TH over delta T, which is, of course, the inverse, which means that efficiency can very easily be over 100%, which means you are using a lot less energy to move a lot more heat. It also means that the smaller the difference in temperature, the more efficient it is, which is very important for practical applications because if you were living in somewhere like Antarctica, you wouldn't probably want to use a heat pump. But if you're living on the beach in California, it's pretty efficient. Now let's return to a more realistic scenario with a pump that runs at 25% of the Carnot efficiency, which would be the maximum efficiency possible, heating a house with 40 megajoules a day. Temperature outside is an average of 45 degrees Fahrenheit, and the temperature inside is ideally 70 degrees Fahrenheit, at least if that's how you'd like to set it. So, our temperature difference then is going to be 13.889 Kelvin, which of course we use Kelvin and convert both the 45 degrees Fahrenheit and the 70 degrees Fahrenheit, as we would not like to use Fahrenheit for calculations involving temperature. That is because if it was some negative degree Fahrenheit outside, then you would severely break these equations and they wouldn't work properly. Our eta of the pump in an ideal situation would then be 294.261 Kelvin over 13.889, which gives you 21.187 or 2118.7% efficiency. Now, of course, this isn't a very ideal situation, so we multiply it by 0.25 and we still get 529.67% efficiency. For 40 megajoules of heat, we divide it by 5.2967, and we get that we only need 7.5518 megajoules of energy to move 40 megajoules of heat from a colder outside temperature to a warmer inside temperature. Now, this is a very good situation to be in because we can already tell that 7.5 megajoules is a lot less than 44.4. But in most situations, a heat pump is going to be running off of electricity, whereas a heating furnace would be running off of burning fuel directly. So, what is the cost of electricity going to be in this situation? Now, considering that this is California, we have that the daytime emission is zero point 0.2 kilograms of CO2 per kilowatt hour, and the nighttime emission is zero point 0.4 kilograms of CO2 per kilowatt hour. We can also simply Google that the average day in California is 4.5 hours longer than the night. So, for our daytime hours, we'll have 16.5, and our nighttime hours will have 7.5. The energy per hour is 7.5518 megajoules over 24 hours, which comes out to 0.31466 megajoules per hour. We can then multiply our daytime and nighttime hours by these values to get that. In the daytime, we produce 5.1919 megajoules, and in the nighttime, we produce 2.3599 megajoules. We can easily convert megajoules to kilowatt hours because a watt is a joule per second. So all we have to do is a unit conversion. And what we get is that we have 1.4422 kilowatt hours during the day and 0.65553 kilowatt hours during the night. So we can multiply these by our emissions per hour on both daytime and nighttime. And what we get is that we produce 0.551 kilograms of CO2, which is about half as much CO2 as you produce by using the furnace, as it would produce 1.11 kilograms of CO2,